Industrial facilities use steam both for heating and for performing various process operations. As the steam gives up heat, it cools and forms droplets of water called condensate. Accumulated condensate in a steam system's piping can cause a number of costly problems. So to maintain efficient, reliable operation of a steam system, condensate must be removed without allowing valuable steam to escape. A device that's commonly used for this purpose is a steam trap. Steam is a vapor that's formed from water. The condensate that's formed as steam cools is a liquid that's heavier than the steam. In a steam system, the relatively heavy condensate will drain to the system's low points. So steam traps are usually installed at these locations to remove the condensate. Removing the condensate is important because accumulated condensate in a steam system can cause a number of problems. Under low temperature conditions, condensate can freeze in piping, resulting in damage such as burst pipes and costly shutdowns. Accumulated condensate can also cause water hammer. Water hammer is the condition that occurs when condensate is carried along with the steam inside a system's piping and slams into the wall of a pipe, particularly around bends. This action can break or crack the pipe. Condensate that builds up in a steam system's pipes also impedes the transfer of heat from the steam and takes up space that could otherwise be occupied by steam. Both of these actions reduce the efficiency of the steam system. Two types of steam are normally associated with industrial steam systems. One type is live steam, which is the steam that's used for heating or for process operations. Live steam is produced by heating water to the appropriate saturation temperature. The saturation temperature is the water's boiling temperature for an existing pressure. Another type of steam that's associated with industrial steam systems is flash steam. Flash steam is normally produced when sufficiently hot condensate that's under relatively high pressure is discharged to the atmosphere or into a lower pressure line. The decrease in pressure causes some of the discharged hot condensate to flash into steam. The production of flash steam when a steam trap discharges is generally a normal part of trap operation. Steam traps must also be able to remove air and non-condensable gases that could build up in the trap and keep it from working. Air and other gases also make a trap more susceptible to corrosion. For example, carbon dioxide is one of the most common non-condensable gases in steam systems. When carbon dioxide mixes with condensate, carbonic acid, which can corrode metal pipes and trap components, is produced. To maintain system efficiency, a steam trap must be able to remove condensate, air, and other gases quickly. The trap must also be able to respond promptly to changing conditions in the system. In most facilities, the rate at which steam condenses in a system varies considerably. If the steam traps in the system can't effectively respond to these variations, the traps will either discharge live steam or they'll leave condensate in the steam lines. Both of these situations can create problems and reduce system efficiency. A steam trap is usually an integral part of a steam trap station, which includes one or more steam traps, as well as associated valves, piping, and related components. In turn, multiple steam trap stations may be used to remove condensate from a facility's steam system. We'll use this illustration to provide an overview of the components that are included in a typical steam trap station. A drip line connects to the lowest point of the steam line or process equipment through which live steam moves. Condensate collects in the drip line. A typical drip line also includes a dirt pocket to trap some of the larger particles of dirt or scale that may be dislodged in the steam lines or the drip line. An inlet valve isolates the steam trap inlet from the steam line. A strainer near the inlet valve prevents dirt and scale from entering the steam trap. A blowdown valve on the strainer can be opened to enable the strainer to be cleaned or blown down by directing flow back through the strainer to the atmosphere. The next component is the steam trap. It drains condensate from the system while preventing the escape of live steam. It may also remove non-condensable gases and some air. Downstream of the trap is a test connection with a valve. The test valve can be opened to see whether the fluid that the trap is passing is steam or condensate. An outlet valve separates the steam trap from the downstream piping. The inlet valve and the outlet valve are isolation valves that can be used to block off or isolate the steam trap from the steam line. This is usually necessary when the trap must be repaired or replaced. A bypass line is also included in many steam trap stations. A valve in the bypass line enables workers to bypass the entire steam trap station if necessary. The bypass valve is usually opened when there is a suspected problem with the trap. Opening the valve may be necessary to keep the facility operating, but as long as the bypass valve is left open, steam blows through the bypass and the efficiency of the steam system is reduced. Sometimes a steam trap is installed in the bypass line. Then, if the main trap fails, the bypass trap can be put into service, and the problem of blowing steam through the bypass line is eliminated. Mechanical steam traps operate in response to the difference in density between steam and condensate. One common type of mechanical steam trap is an inverted bucket, or IB trap. The trap is named for the open float that's contained in the trap's cylindrical casing. The float is a bucket-shaped device that's been inverted or turned upside down. The top of the inverted bucket has a small hole or vent that allows air and non-condensable gases to leave the bucket and collect in this part of the casing, which is sometimes called the cap. The top of the inverted bucket also has a clip that's attached to a connecting rod. The rod connects the bucket to the trap valve. During proper operation of the trap, the casing is filled with condensate to a level that's just above the top of the bucket. This level of condensate is called the prime. The prime provides a water seal that prevents live steam from escaping the trap under the bucket. At startup, the bucket, which we've cut away, rests at the bottom of the casing, and the trap valve is fully open. Condensate from the steam system drains into the trap and flows under the bottom of the inverted bucket. The condensate passes between the outside of the bucket and the inside wall of the casing. The small vent in the top of the inverted bucket allows condensate to collect in the trap without lifting the bucket. As long as the trap is full of condensate, the bucket remains at the bottom of the casing, and the trap valve stays open. The condensate flows through the valve to the trap outlet. When steam enters and accumulates to fill about 2/3 of the bucket floats, and the trap valve closes, so no more condensate discharges. While the valve remains closed, air and non-condensable gases, which are less dense than the condensate, pass through the bucket's vent and collect in the cap area of the casing. Meanwhile, more condensate enters the bucket, and some of the steam in the bucket condenses. When only about 1/3 of the volume of the bucket is filled with steam, the bucket drops, and the trap valve opens. Accumulated air is discharged first, then condensate. The flow of condensate under the bottom of the bucket picks up dirt and sweeps it out of the trap. Condensate continues to discharge until more steam floats the bucket and the cycle repeats. Because an inverted bucket trap works on a cycle, the trap has an intermittent discharge. Accumulated steam closes the trap valve, so there's no discharge from the trap, although condensate continues to drain into it. Accumulated condensate opens the valve so that the condensate can be discharged from the trap. The open float in an inverted bucket trap makes the trap resistant to water hammer. Inverted bucket traps are also able to handle air and other non-condensable gases because these gases are less dense than condensate. However, the vent in the top of the bucket is small, and only a correspondingly small amount of air can pass through it. So to avoid problems, inverted bucket traps generally should not be used if large volumes of air must be removed. A leaking trap valve is a common problem that can cause an inverted bucket trap to fail. The leak is often the result of damage or wear on the valve or the valve seat. If the valve doesn't seat properly, it will leak, and the trap may fail open, that is, with the trap valve in the open position. The trap will also fail open if the bucket becomes disconnected from the rod that connects it to the trap valve. Also, freezing and the damage it causes can be a problem with an inverted bucket trap, because normally the trap always contains some condensate. To prevent freezing, inverted bucket traps that will be shut down for a significant length of time should be drained. This is a float and thermostatic, or F&T trap. It's generally classified as a mechanical trap because one of its major internal parts is a ball-type float mechanism for removing condensate. However, it also has a thermostatic bellows that reacts to changes in temperature and is used to remove air and non-condensable gases. So in this respect, the trap is thermostatic. More information about thermostatic traps is given in the part of this topic that's entitled Thermostatic Traps. For now, let's look at how a typical F&T trap works. As condensate enters the trap, the accumulating condensate lifts the ball-type float that's attached to the trap's main valve. This action opens the main valve and allows the condensate to flow through the trap outlet. When steam enters the trap and reaches the bellows expands and the vent valve closes. At the same time, with the main valve open, condensate continues to flow through the trap and be discharged. The changing level of the condensate causes the float to rise and fall, which in turn affects how wide the trap valve opens and how much condensate is discharged. The buildup of air and gases in the trap lowers the temperature and eventually causes the bellows to contract, which opens the vent valve. Then, the air and gases are discharged through the trap outlet. The reaction of the bellows to temperature changes enables air and non-condensable gases to leave the trap and keeps the trap from becoming airbound. Air binding, or becoming airbound, is the condition that results when air fills a trap, closing the trap valve and keeping the trap from operating. If operating conditions cause condensate to build up to the point that the trap becomes waterlogged, the relatively cool condensate causes the bellows to contract, which opens the vent valve. Then the condensate drains through the open vent to the trap's discharge line. Dirt accumulated below the trap valve can cause an F&T trap to fail because large dirt particles can restrict the movement of the float mechanism. Failures caused by accumulated dirt particles can usually be avoided by installing a strainer at the trap inlet. Also, F&T traps can fail if water hammer or high pressures cause the trap's float to collapse. Other common problems that may be associated with F&T traps include disconnection of the float from the trap valve and damage from freezing if condensate isn't drained from the shutdown trap. In this part, we'll look at the operation of thermostatic steam traps. A thermostatic trap operates in response to the differences in temperature between steam, condensate, and air. One of the most common types of thermostatic traps is a bellows trap, which gets its name from the thermostatic bellows that is the trap's main internal component. At startup, the bellows is fully contracted and the trap valve is wide open. Condensate and air are pushed ahead of the steam directly through the trap outlet. Once steam enters, the temperature in the trap increases and the bellows quickly expands. As the bellows expands, the trap valve closes, and steam is prevented from escaping. But as more condensate enters the trap and contacts the bellows, the relatively cool condensate causes the bellows to contract. As the bellows contracts, the valve opens and condensate leaves through the trap's outlet. Air and other non-condensable gases are usually cooler than steam, so they also cause the bellows to contract, which opens the valve and allows the gases to escape along with the condensate. A disadvantage of a bellows trap is that it generally can't be used in situations where pressures are very high because the bellows might collapse. Another disadvantage is that water hammer can rupture the bellows and cause the trap to fail. At any given temperature, the two different metals in the element expand and contract at different rates from each other. This causes the element to bend back and forth as temperature changes occur. Cool condensate, or air, bends the bimetal element one way to open the valve, and steam bends the element the other way to close the valve. Since the valve of a bimetallic trap is fully open when the trap is cold, this type of trap is effective during equipment startup because the trap can quickly eliminate air and cold condensate. But the trap response is more sluggish when steam has reached normal operating temperatures because time is required for the dissipation and absorption of heat that opens and closes the trap valve. Most thermostatic traps discharge condensate intermittently. The time it takes for condensate to discharge depends on the amount of condensate in the trap's drip line. The more condensate there is, the less time it takes to cause the trap to discharge. Thermostatic traps are also excellent at removing air. In this part, we'll look at thermodynamic steam traps. A thermodynamic trap contains a component such as a disc or a piston that responds to variations in velocity and pressure that are related to changes in state of the incoming fluid. We'll look at a typical disc-type thermodynamic trap. This example is a tilting disc trap. It's designed to handle low to medium condensate flow. As its name suggests, the trap contains a disc that lifts or tilts. The disc is the trap's only moving part. At startup, the disc rests on seating surfaces that contact the trap's inlet and outlet. With the disc in this position, the trap is closed. When relatively cool condensate enters the trap, the flow lifts the disc up and opens the trap. The condensate then flows through the outlet and is discharged. During normal operation, hot condensate entering the trap experiences an increase in velocity and a reduction in pressure. As a result, some of the liquid condensate changes state, flashing to steam. Because steam has a greater volume than an equivalent weight of condensate, the velocity of the flow through the trap greatly increases after the flash steam has been generated. This further increase in velocity reduces pressure on the underside of the disc. At the same time, flashing condensate flows out and causes a pressure buildup in the area above the disc. When sufficient pressure builds up here while pressure on the underside of the disc has been reduced, the disc is forced down onto the seating surfaces, which closes the trap. The disc is held closed by the pressure of the steam that's in the chamber above the disc. When this steam condenses, changing to a liquid state, and the pressure above the disc becomes low enough, the disc rises and condensate flows out, until velocity and pressure conditions within the trap again cause the disc to snap down on the seating surfaces, closing the trap. If the temperature and pressure at the trap inlet remain constant, a disc trap opens and closes at regular intervals. That is, the trap operates on a time cycle. Because it operates on a time cycle, as long as the temperature and pressure at the trap inlet remain constant, a disc trap stays closed for the same amount of time, typically 5 to 10 seconds, each time that it closes. Condensate that comes to the trap in the middle of a time cycle won't be discharged until the pressure above the disc falls low enough to allow the disc to rise and reopen the trap. Since the movement of the disc cycles between the open and the shut positions, the discharge from the trap is intermittent. Many of the maintenance problems associated with thermodynamic steam traps are due to wear of the trap components. Thermodynamic traps are very sensitive to scale or dirt that gets lodged on the seating surfaces. For this reason, a strainer should always be installed at the trap inlet. The strainer should be cleaned or blown down frequently to be sure that it remains free of debris and does not become clogged. Thermodynamic traps that are exposed to adverse weather conditions, such as rain, may begin to cycle more frequently than normal. When this happens, the moving parts of the trap wear out faster simply because they operate more frequently. Manufacturers provide various solutions to this problem. Some manufacturers make thermodynamic traps with double-walled bodies. Steam or condensate that enters a double-walled trap first flows around the outside of the internal parts and then into the trap. The warm condensate or steam keeps the internal parts at a relatively even temperature. Another way to protect a trap from adverse weather conditions is to use a bonnet cover. The bonnet is the top of the trap casing, and a bonnet cover is a metal cap that's placed over the top of the trap. The airspace between the cap and the trap body acts as an insulator and protects the trap from the weather. An important part of the maintenance of a steam system is surveying the steam trap stations within the system. Surveying is the process of inspecting equipment to detect problems or malfunctions. Different problems may become evident as the various pipes, valves, traps, and strainers in a steam trap station are checked. Before you begin to survey a trap station, you should familiarize yourself with the normal operation of the steam system in which the station is installed. Make sure that the system's steam is pressurized and is reaching the trap station. You also need to know whether the system normally has a constant steam flow or a modulating or varying steam flow, because the type of flow affects steam pressure. It's important to check both the pressure and the temperature of the system's steam. First, note the steam pressure and temperature at the inlet for the equipment to which the system is supplying steam. Then compare these values with the recommended temperature and pressure for the equipment. Usually, if the pressure or temperature isn't within the recommended limits at the equipment inlet, the pressure or temperature at the trap in the trap station will also be incorrect. Whenever this occurs, the source of the problem should be traced, so corrective action can be taken. Another essential task in a trap station survey is checking pipes for damage and leaks. You should also make sure that the drip line is connected to the lowest point in the steam system. The drip line must be sloped toward the trap to avoid pockets that might cause sluggish condensate flow. The slope also ensures that gravity will keep condensate from building up in the line and causing water hammer. The drip line must also be large enough to carry the volume of condensate that's being produced. It should never be smaller than the trap inlet. Often, condensate from a trap discharges into a return line, which should be checked during a trap station survey. The condensate return line may be elevated, as it is in this installation, or it may be placed low so that condensate can drain from it by gravity. Either way, the condensate return line must be large enough to carry the total volume of both the condensate from the trap and any flash steam that's formed. Generally, a condensate return line should be at least as large as the trap outlet. The back pressure at the trap outlet should be checked to make sure that it's not too high. If there's no gauge downstream of the trap, you may need to install a temporary gauge so you can check the back pressure. For most thermodynamic traps, the downstream pressure should not exceed 70% of the upstream pressure, but the manufacturer's instruction should be checked for the allowable back pressure for a particular trap. Increased back pressure will cause the trap to cycle open and closed more frequently, and it also reduces trap capacity. Likewise, if several thermodynamic traps discharge to a common return line, it's essential to make sure that the condensate return line is large enough to handle simultaneous discharge without developing excessive back pressure. For other traps, like this inverted bucket trap, increased back pressure may reduce trap capacity, but it doesn't otherwise significantly affect trap performance. Another task that's usually part of a trap station survey is making sure that the trap strainer has been blown down. If this hasn't been done, opening the strainer blowdown valve one full turn and then closing it will usually provide enough flow to clean out the strainer. Finally, you should keep a record of the trap station's performance or operating history. Reviewing the operating history may reveal specific problems that should be checked during a survey of an individual trap, or it may clear up questions about how the trap station has performed under certain operating conditions. After a steam trap station has been surveyed or inspected, the next step is to survey the individual traps in the station. Trap problems aren't always easy to detect, so a combination of different inspection methods may be used. Typically, a thorough trap survey combines information obtained by performing 3 types of inspections: temperature, sound, and visual. A temperature inspection is usually a good starting point for a trap survey. The temperature at the trap's inlet and outlet pipes should be in the normal range for the specific trap installation. Generally, the inlet should be hotter than the outlet, but if the outlet is cold, it could indicate that the trap has failed closed. Whatever method you use for a temperature check, you must be able to interpret the meaning of the information that you obtain. For example, a properly functioning steam trap is usually warm because live steam is unable to escape from the trap, while a cold trap is probably not working. However, a trap normally operates somewhat cooler when it's working properly than when certain malfunctions occur. For instance, a significant increase in the temperature of the trap could indicate that the trap has failed open and live steam is escaping. If the trap inlet temperature is in the allowable range, trap inlet conditions are normal, but this doesn't mean that the trap outlet conditions are also normal. Outlet conditions must be checked separately. If the temperature at the trap outlet is also within the allowable range, trap conditions are probably normal for the temperature inspection part of the trap survey. Trap surveys based on differences between trap inlet and outlet temperatures can be inaccurate in certain situations. For instance, if a series of traps are installed on a manifold setup so they discharge to a single return line, back pressure may rise because of faulty traps. But the back pressure will rise on all the traps in the system, good and bad alike. So a temperature inspection alone probably won't give reliable information about the condition of a specific trap. On the other hand, in piping systems that have sufficiently large return piping, a failed trap may cause no rise in back pressure, and the temperature differential would remain unchanged. So this is another situation in which measuring the temperature differential across the trap won't detect the trap failure. Another type of trap inspection is a sound inspection. It's performed by listening near a trap's outlet for mechanical sounds and flow noises that are associated with the operation of the trap. To perform an accurate sound inspection, you generally need to use some type of listening device. The device carries the sound from the trap to your ear and helps filter out background noise from other traps, pumps, and similar equipment that can make it difficult to obtain a reliable reading. Even with the help of a listening device, filtering out noise is especially difficult if several traps in a manifold discharge to a single header, because sound can travel from trap to trap through the piping, and a good trap could be telegraphing or conveying the signal of a malfunctioning one. So if you detect the sound of a malfunctioning trap while you're performing a sound inspection at a trap manifold, keep in mind that the failed trap is usually the one that's producing the loudest signal. However, not even the most sophisticated listening device can help you detect trap problems if you don't know what sounds you should be listening for. Each type of trap has its own particular sounds during normal operating cycles and during failure. With training and practice, you'll be able to recognize the differences between the sound of a trap that's discharging normally and one that's not. Also, when an ultrasonic detector is used to inspect a steam trap, the frequency response of the detector may vary by model and manufacturer. These variations can affect the actual sound that you hear from a trap. But listening to a few examples of typical trap sounds will give you some guidelines that you can apply on the job. A visual inspection can be a very informative part of a steam trap survey. But as with other types of inspections, you need training and practice to be able to perform the inspection effectively. Begin by simply looking over the trap for condensate or steam leaks. Leaks typically occur at piping connections and at the steam trap's body-to-bonnet connections. Next, see if live steam is being discharged from the trap. This is relatively easy to determine if the trap discharges to the atmosphere. Of course, before you can determine if a trap is discharging live steam, you must be able to recognize the difference between flash steam and live steam. Flash steam is a normal condition in which vapor is formed when hot condensate is discharged from a trap. Normally, the discharge from a trap consists of a center core of hot condensate with a slowly moving white cloud of flash steam circling the outside. Live steam is produced in the steam system's boiler. It's usually discharged with more force than flash steam is, and it has no center core of hot condensate. If it's working properly, a steam trap should be discharging hot condensate with some flash steam. But if it's discharging live steam, the trap isn't working properly, and it must be repaired or replaced. If the discharge is intermittent, the cycle rate should be timed, and the time should be compared with the cycle time that your facility or the manufacturer lists as normal for that particular trap. Different traps have different discharge cycle rates. Disc traps, for example, are designed to discharge intermittently, so a continuous discharge could indicate serious problems. Float and thermostatic traps, on the other hand, are designed to discharge condensate continuously, as long as there's a constant flow of condensate into the trap. And although an inverted bucket trap usually discharges condensate intermittently, it may have a constant small discharge if it's operating at a very low percentage of its rated capacity. This condition is sometimes called dribbling. By combining the information you get from performing temperature, sound, and visual inspections that you make during a trap survey, you can get a good idea of how well a specific trap is working. Trap surveys should be performed on a regular basis. A trap's size, pressure, and workload will determine exactly how often a survey should be conducted. Keep a record of trap performance as an aid for determining if a trap has a high failure rate. A trap that fails several times within its normal service life should be investigated. The failures could be a sign that the trap was installed incorrectly, or that the wrong type of trap is being used for the application. In most facilities, steam traps are removed from service and replaced as part of normal preventive maintenance. Traps are also replaced when they fail or malfunction. Sometimes a worn or damaged trap can be repaired. In other cases, damaged traps must be replaced with new ones. Either way, you must follow your facility's procedures and take all the appropriate safety precautions. The exact procedure that you should follow to replace a steam trap depends on the specific trap installation that you're dealing with. But certain major steps are common. We'll look at a typical procedure for removing worn components from an inverted bucket trap and installing new replacement components so the trap can be returned to service with minimal downtime. First, close the appropriate valves to isolate the trap. Next, drain the lines and allow the trap to cool down. Then, follow your facility's procedures to lock out and tag out the trap. The body of this trap is made in two parts. One part is a cap, and the other is a cylindrical casing that the cap is bolted onto the top of. To inspect and repair the trap, we must remove it from the system piping. Unbolt the cap, then remove it, along with the operating mechanism and the bucket, which are attached to the inside of the cap. Remove the old gasket and discard it. Clean the gasket sealing surface thoroughly to prepare it for installation of a new gasket. Clean accumulated sediment from the trap body and its passages. Check the body of the trap for corrosion, especially at the inlet and outlet passages. The body of the trap, in our example, is in good condition, so it doesn't need to be replaced. Now examine the cap and the operating mechanism. If the cap is corroded, it must be replaced. Also, check the bucket for any wear or damage. Inspect the linkage, the valve, and the seat of the operating mechanism. In this case, the valve seat is worn and will have to be replaced. Now, install the required replacement parts, including a new gasket. Because manufacturers usually sell the valve and the seat as a single assembly, you should replace both the valve and the seat whenever either one of these parts is damaged. Finally, follow your facility's procedures to install the repaired trap and bring it back online. If you must replace an old or damaged trap with a completely new one, be sure that the new trap is the right size for the installation. A trap that's too large remains closed for the same amount of time as a properly sized trap because closing time is based on the rate of condensate accumulation, which depends on how fast the steam is condensing, not on the size of the trap. But an oversized trap can discharge condensate faster, so it opens for a shorter length of time than a properly sized trap. Over the same time period, then, an oversized trap will open and close more frequently and consequently wear out faster than a properly sized one. On the other hand, a trap that's too small won't be able to handle all the condensate that's formed. This could lead to water hammer in the drip lines, or more likely, in the steam system that's being drained. What does this type of discharge usually indicate about the condition of a steam trap?